Space is silent. That's what you've been told, and it's true and also completely wrong. NASA has released recordings from the edge of our solar system, from black holes hundreds of millions of light years away, and from planets with no air to carry a single wave. None of it should exist, all of it does. We go from the recordings NASA insists are real, to the ones that were never sound at all, to the one signal that blurs the line between the two, and won't let you think about silence the same way again. One thing before we begin, if you're the kind of person who needs to know what's real before they believe it, subscribe. It helps us reach more minds like yours. We're genuinely glad you're here. Now, let's begin. Sound is not light. Light can cross a vacuum without any help. It doesn't need anything to carry it. It simply travels alone through nothing at all. Sound can't do that. Sound is a pressure wave. It's a chain reaction of molecules bumping into each other, one after another, passing energy down the line like a crowd doing the wave in a stadium. Take away the crowd, and there's nothing left to pass along. That's the whole problem with sound in space. Not that space is too big, or too cold, or too strange, just that most of it doesn't have the one ingredient sound actually needs, something to push against. Here's the number that makes this concrete. On Earth, at sea level, every cubic centimeter of air contains about 25 quintillion molecules, 25 followed by 18 zeros, packed into a space smaller than a sugar cube. That density is what lets a trumpet blast reach the back row of a concert hall, what lets your voice cross a room, what lets thunder roll for miles after a lightning strike. Now go a few hundred kilometers above your head into what's normally called space. The molecule count in that same cubic centimeter drops to somewhere around a few hundred, not a few hundred quintillion, a few hundred, full stop. It's not empty. Very little in the universe is ever perfectly empty, but it's close enough to empty that sound, as your ear would recognize it, simply can't survive the trip. This is where the popular version of the story usually stops. Space is silent. Full stop, end of sentence, moving on. And as far as it goes, that's correct. Nobody has ever floated in open vacuum and heard anything at all, and nobody ever will, because there's nothing there to hear it with either. Your eardrum works exactly like a tiny speaker cone, and a speaker cone with no air to push against is just a piece of plastic vibrating uselessly in the dark. But space is silent, quietly does something that a lot of misconceptions do. It treats space as if it's one uniform thing. It isn't. The interplanetary space between Earth and Mars, the atmosphere clinging to Saturn's largest moon, the interior of a comet's tail, the 100 million degree gas sitting inside a galaxy cluster 240 million light-years away. These are wildly different environments, and some of them are far from empty. Some of them are dense enough, turbulent enough, or electrically active enough that they can carry something very close to real sound, not all the way to your ear, not without help. But close enough that spacecraft have recorded it, scientists have decoded it, and NASA and ESA have released it to the public as audio you can press play on right now. There's a reason this myth took hold so firmly in the first place, and it isn't purely scientific, it's cultural. For decades, science fiction has treated the vacuum of space as a canvas for sound design rather than a physical environment with actual rules. Explosions roar. Starships whoosh past the camera. Laser blasts crack through empty vacuum as if it were a canyon. Audiences grew up on that sound, learned to expect it, and eventually a kind of backlash formed, a wave of documentaries and articles insisting, correctly, that real space doesn't work that way, that a ship exploding in true vacuum would do so in total silence. That correction was accurate. But like a lot of corrections, it overshot. Hollywood space sound is fake, quietly became, space has no sound, ever, anywhere, and that second claim is simply too broad to survive contact with the actual solar system. Consider the scale problem for a moment, because it helps explain why the myth is both right and wrong at the same time. Sound on Earth travels at roughly 343 meters per second through air at room temperature, fast enough that thunder from a nearby lightning strike reaches you in seconds, slow enough that you can time the gap and estimate the storm's distance. That speed depends entirely on the density and temperature of the medium it's moving through. Change the medium, and the speed changes with it. Sound moves nearly 5 times faster through water than through air, and faster still through solid steel. Remove the medium entirely, and there's no speed left to calculate because there's nothing left to move. Between 343 meters per second through Earth's atmosphere and no speed at all. Because there's no medium, lies an enormous range of environments most people never think to place on that spectrum. Titan's thick nitrogen haze Mars's thin, but real atmosphere, the hot ionized gas, inside a galaxy cluster, the sparse, but non-zero particles drifting through interplanetary space on the solar wind. None of those environments is a textbook vacuum. Each one can carry something, even if what it carries doesn't always look like sound the way your ear expects it to. That's the real shape of this story, and it's more interesting than either extreme. It's not space is totally silent, and it's not space is full of ghostly alien noise, either, whatever certain corners of the internet would have you believe. It's a spectrum. On one end you have places where actual sound waves exist and get recorded the way a microphone records anything, real vibration, real pressure, real air. On the other end you have places so empty, so violent, or so far outside the range of human hearing that scientists have to translate something else entirely, X-rays, radio waves, electric field fluctuations, into a signal your ears can interpret. Both of these get called the sounds of space. Almost nobody explains which is which. That confusion is exactly where the myths take root, and it's exactly where we're going to spend the next 2 hours pulling them apart, one recording at a time. We're going to start close to home, with the only 2 worlds in the solar system, besides Earth, where something that can honestly be called sound has actually been captured. Then we're going to move outward, into environments where sound stops meaning what you think it means, and where the line between recording and translation gets blurry enough that even scientists argue about the right word to use. By the time we reach the far end of that spectrum, we'll be listening to something that started as X-ray light from a black hole 240 million light-years away, and ended up after a scaling factor almost too large to say out loud, sounding uncannily like a human voice. But we start smaller. We start with wind. If you had to guess how many worlds in the solar system have an atmosphere thick enough to carry sound the way Earth's does, you'd probably undercount. Most people picture the solar system as one habitable planet surrounded by a collection of airless rocks and gas giants too hostile to matter. That picture is wrong, or at least badly incomplete. Venus has an atmosphere so dense that sound actually travels through it more efficiently than it does through Earth's air. A bell rung on the surface of Venus would ring far longer and far lower than the same bell rung here. Titan, Saturn's largest moon, has an atmosphere thicker than Earth's, made mostly of nitrogen, with enough pressure at the surface that a person standing there, heavily insulated against the cold, could, in principle, shout and be heard. And Mars, the planet most people write off as basically airless, has an atmosphere about 1% as dense as Earth's. Thin, genuinely thin, but not zero. That 1% turns out to matter enormously, because 1% of an atmosphere is still an atmosphere, and any atmosphere at all is a medium sound can use. The myth of absolute silence usually gets built on an image of Mars as more or less identical to the Moon, a bare, cratered surface with nothing overhead but black sky. The Moon really is close to a true vacuum at its surface, thin enough that Apollo astronauts could only hear the Moon through vibrations conducted directly into their suits, never through open air. Mars is a different case entirely. Mars has weather. Mars has wind. And in December of 2018, Mars had a spacecraft sitting on its surface with instruments sensitive enough to notice. Titan and Venus, for their part, remain almost entirely unexplored acoustically, despite having atmospheres more than capable of carrying sound. Venus's surface pressure is roughly 90 times that of Earth, closer to the pressure, a kilometer deep in Earth's oceans, than anything found on a planetary surface, and its atmosphere is so dense that sound moves through it with unusual efficiency. Low frequencies traveling especially far with very little loss. No human instrument has ever produced a clean, sustained recording of that environment. The handful of landers that reached Venus's surface survived only briefly against pressure and heat that would crush and melt most spacecraft within an hour or two. Titan, colder and gentler by comparison, has been reached exactly once, by exactly one microphone, for exactly one descent. That's the entire acoustic record of a world larger than the planet Mercury. That spacecraft was NASA's InSight lander, and what it captured over the following pages is going to complicate the Silent Mars story permanently. It's worth pointing out that InSight wasn't the first attempt to hear another planet. Space agencies had tried before, and mostly failed, in ways that make InSight's accidental success feel almost improbable by comparison. In the late 1970s and early 1980s, Soviet Venera missions carried microphones down to the surface of Venus, through an atmosphere so crushing and so hot that most landers survived barely an hour before being destroyed by pressure and heat. Some of that audio data survived the trip back to Earth, faint and difficult to interpret, but real. Decades later, NASA tried to send a microphone to Mars aboard the Mars Polar Lander, and lost the entire spacecraft during descent in 1999, the microphone included, along with everything else on board. For close to 20 years after that failure, nobody had a working microphone anywhere near the Martian surface. Mars, as far as human instruments were concerned, stayed conspicuously silent, not because it was silent, but because nothing had survived long enough to prove otherwise. InSight touched down on Mars on November 26, 2018, in a flat, unremarkable region called Elysium Planitia, chosen precisely because it was unremarkable, safe, and stable, ideal for a mission built to study the planet's deep interior rather than its surface. InSight wasn't designed with sound in mind at all. Its primary instrument, a seismometer called SCIS, was built to detect Marsquarks, vibrations traveling through the planet's rock, the way seismometers on Earth detect earthquakes. Its secondary instrument, an air pressure sensor that was part of a package called APSS, was built to track Martian weather, temperature swings, dust devils, the slow rhythm of a planet's daily breathing. Neither instrument was supposed to record something you could listen to. And then on December 1st, 5 days after landing, both of them accidentally did. Winds of somewhere between 10 and 15 miles an hour moved across the landing site, blowing from the northwest toward the southeast, a direction that matched dust devil tracks scientists had already spotted from orbit. Those winds pushed against InSight's two enormous solar panels, each over 2 meters wide, sticking out from the lander's sides like a pair of open ears. The panels flexed, almost imperceptibly, under the pressure of the moving air. The seismometer, sensitive enough to detect ground motion measured in nanometers, picked up those flexes as vibration. At the same time, the air pressure sensor recorded the actual pressure fluctuations directly, the same physical phenomenon your eardrum responds to when someone speaks across a room. Bruce Bannert, the mission's principal investigator at NASA's Jet Propulsion Laboratory, called it an unplanned treat. It's a modest way to describe something that had never happened before, a working recording of wind, captured live, on the surface of another planet. The recording itself needed some translation before human ears could make sense of it, not the deep, cross-domain translation we'll run into later with black holes, but a much smaller adjustment. The seismometer's raw signal sat right at the very bottom edge of human hearing, close to 50 hertz, quiet and difficult to make out on ordinary speakers. NASA released that raw file untouched and also released a version shifted up 2 octaves, simply to make it easier to hear on a laptop or a phone. The air pressure sensor's data ran even lower, close to 10 hertz, below what most people can consciously perceive as pitch rather than pulse, so NASA sped that one up by a factor of 100, again purely to bring it into audible range. In both cases, the underlying phenomenon was already sound in the truest sense: real air, real pressure changes, real physical vibration recorded by real instruments. The only thing that changed for human ears was the pitch, not the nature of the signal itself. What you hear when you listen to it is a low, hollow, breathy rumble, something between wind moving past a microphone and the muffled sound of being underwater. Don Banfield, the scientist who led the air pressure investigation, described it as reminding him of sitting outside on a windy afternoon, listening to gusts pass by. That's not a metaphor built for a documentary. That is physically, essentially what it was: wind recorded honestly from 140 million miles away. Compare that to what a similar gust sounds like moving through Earth's atmosphere, and the difference is immediately obvious, not in kind, but in character. Earth's air is roughly 100 times denser than Mars's, and that density difference changes everything about how a given gust of wind actually sounds. A 15-mile-an-hour breeze on Earth produces a bright, textured hiss, full of high-frequency detail as air rushes past leaves, wires, the fine structure of any object it touches. The same wind speed on Mars, moving through 100th as much air, loses almost all of that high-end texture. What's left is closer to a deep, muffled pulse, the low frequencies surviving where the high ones simply don't have enough medium to carry them. Scientists sometimes describe it as sounding like being underwater for exactly this reason. Water, like Mars's atmosphere, tends to absorb high frequencies far more aggressively than air does, leaving only the low rumble behind. This is worth sitting with for a moment, because it quietly breaks the cleanest version of the silent Mars myth. Mars has almost no magnetic field to speak of. Its atmosphere is 100 times thinner than Earth's. Its skies, in nearly every photograph ever taken, look catastrophically empty. And it still provably has sound, real sound, in the traditional physical sense, because almost no atmosphere and no atmosphere turn out to be very different categories. It took a mission specifically designed to feel the planet's pulse, rather than photograph its surface to prove it. But Mars isn't even the most striking example in the solar system. For that, we have to go much further out, to a moon so cold that its rivers run with liquid methane instead of water, and so thick with haze that no camera had ever seen its surface clearly, until a spacecraft descended through it in silence carrying a microphone nobody was sure would work at all. On January 14, 2005, a small, saucer-shaped probe called Huygens separated from its mothership, the Cassini spacecraft, and began falling toward the surface of Titan, Saturn's largest moon. It took roughly 2.5 hours to descend through Titan's thick orange, nitrogen-rich atmosphere, an atmosphere so dense and so cold that engineers had spent years debating whether Huygens would land on solid ground, sink into liquid, or simply crumple against a surface no one had ever seen clearly because Titan's haze is opaque even to cameras in orbit. Huygens carried an instrument called HASI, the Huygens Atmospheric Structure Instrument, built primarily to measure temperature, pressure, and the electrical properties of Titan's atmosphere as the probe fell. Almost as an afterthought, HASI included something unusual for a planetary probe, a working microphone mounted on the outside of the spacecraft, designed originally to listen for the telltale crack of lightning inside Titan's clouds. If Huygens happened to fall through a thunderstorm, scientists reasoned, the microphone might catch the thunder, while the instrument's electrodes caught the lightning's electrical signature at the very same moment, giving them a way to measure exactly how close the storm had passed. Huygens never found a thunderstorm. What it found instead for 2.5 hours was the ordinary sound of falling through an alien sky, the hiss and rush of atmosphere moving past the probes, casing a sound one planetary scientist later compared to sticking your head out of a moving car window. Except the window was 100 million miles from home, and the air outside was cold enough to freeze methane into rain. After landing softly, in what turned out to be a damp, sludge-like surface somewhere between mud and wet sand, the sound changed again, dropping into something quieter and more contained, largely internal to the microphone itself as Huygens finally came to rest. Because of the enormous distance and Huygens' limited power and transmission time, the probe didn't send back a smooth, continuous stream of raw audio. It sent back compressed packets of data describing the sound, which scientists on Earth then had to reconstruct, stretching the information back out into something continuous enough for a human ear to follow. That reconstruction work was done quickly, in the hours and days after landing, so the public could hear it almost as soon as scientists themselves could. What matters here isn't the reconstruction step. Plenty of ordinary audio recording involves some digital processing before it reaches your ears. What matters is what was being reconstructed, a genuine acoustic signal, picked up by a genuine microphone, moving through a genuine atmosphere on a world over 1 billion kilometers from Earth, to date. It remains the only microphone recording ever made during a spacecraft's descent to a world beyond the Earth-Moon system, not a translation of some other kind of data, not a scientific illustration dressed up as sound, but the same basic physical process that lets you hear rain on a window happening on a moon of Saturn. Ralph Lawrence, one of the planetary scientists who worked on interpreting the descent data, later noted that the wind sounds Huygens captured weren't just atmospheric, they carried real scientific information, hints about the thickness and turbulence of Titan's atmosphere layered right into the texture of the noise. The boring sound of wind, as one team member put it at the time, turned out to be scientifically useful precisely because it was real, nothing dramatic, no alien thunder, no unmistakable roar, just the quiet, physical fact of a world with weather, recorded as it happened. Huygens carried something else worth mentioning, something with no scientific purpose at all. Tucked into the probe's structure was a small digital recording of music, 4 themes composed by the French musicians Julien Sivange and Louis Hayeri, sent along essentially as a cultural gesture, a message with no practical function beyond marking the moment. It never played during the descent, and no instrument on Huygens was built to broadcast it outward. It simply rode along in silence, on a probe that spent its final 2.5 hours listening rather than speaking, mapping the sound of an alien atmosphere on its way down, while carrying, unheard, a small fragment of Earth's own. There was a second kind of sound produced during the Huygens descent, and it's worth separating clearly from the wind recording because it points directly toward the world we're about to enter. As Huygens fell, its radar altimeter sent out signals searching for the surface below. And scientists later took the pattern of those returning radar echoes, nothing to do with air or pressure at all, and converted it into an audible track, a rising chirping tone that intensified as the probe closed in on the ground. That recording sounds dramatic. It sounds, if anything, more alien than the real wind captured by the microphone sitting right next to it. But it isn't a recording of anything that ever vibrated through Titan's atmosphere. It's a radar signal, translated into pitch, built for human ears rather than captured by them. Even during a single 2.5 hour descent on a single spacecraft, both categories of sound of space already existed side by side, one real, one translated, and almost nobody listening to either one at the time could have told you which was which. So here's where the story sits, 2 worlds in. Mars, with an atmosphere thin enough that most people assume it's essentially airless, has yielded a real recording of wind, picked up almost by accident by a lander that wasn't built to listen for anything at all. Titan, over 1 billion kilometers further out, has yielded something even rarer, the only microphone recording ever captured during a descent to another world, a genuine acoustic signal from an atmosphere thicker than our own. Between them, they quietly dismantle the flattest version of space is silent, because neither of these worlds is silent, not in any way that would satisfy a strict definition of the word. But notice what both of these places have in common. They have atmospheres. They have air or something close enough to air for a microphone to physically respond to. That's the boundary we're about to cross, and it's a hard one. Somewhere past Mars, past Titan, past every world with enough atmosphere to carry a pressure wave, the microphone simply stopped being useful. Interplanetary space is too thin. Interstellar space is thinner still, trillions of times emptier than the air in your lungs right now. And the objects that produce some of the most famous sounds of space ever released to the public, black holes, galaxy clusters, the churning plasma at the edge of the solar system, don't have anything remotely resembling breathable air anywhere near them. And yet NASA has released audio of a black hole, not a musical interpretation, not a sound effect added for a documentary, audio built directly from real astronomical data, data that scientists insist represents something genuinely physical happening 240 million light-years from Earth. If there's no atmosphere out there, no microphone that could possibly survive the trip, and nothing resembling air anywhere near a black hole, then what exactly are we listening to when we press play? Here's the honest answer, in outline, before we go looking for the details. Nothing was ever recorded, in the sense that a microphone records anything. What NASA actually released is closer to a translation than a recording, a way of taking a real physical measurement, one that has nothing to do with air pressure at all, and mapping it onto sound the way a sign language interpreter maps spoken words onto gesture. The meaning survives the translation, the original form doesn't, and once you accept that distinction, recording versus translation, air versus something else entirely, a whole category of sounds of space starts to make sense that otherwise looks like a contradiction in terms. Consider for a moment everything that could possibly be translated this way. A radio telescope doesn't listen for sound. It listens for electromagnetic radiation, the same category of wave as visible light, just at a wavelength your eyes can't see and your ears were never built to detect. An X-ray observatory does something similar at an even higher energy. A magnetometer measures the strength and direction of a magnetic field moment to moment as a spacecraft passes through it. None of these instruments are microphones. None of them are listening for anything that vibrates through matter the way sound does. And yet every one of them produces a stream of numbers changing over time, rising, falling, oscillating in patterns. And a stream of numbers changing over time is exactly the raw material sound is built from, whether that stream started as air pressure or not. That's the door scientists walked through, starting decades ago and accelerating dramatically in the last 20 years, as sonification tools became fast enough and accessible enough to turn almost any dataset into audio on demand. A magnetic field measurement becomes a pitch that rises and falls with the field's strength. An X-ray brightness map becomes a scan, moving left to right across an image, with each point converted into a tone. A radio signal already technically electromagnetic rather than acoustic gets shifted down or up into the narrow band of frequencies a human ear can actually process. And suddenly something that was never sound in any physical sense becomes something you can genuinely listen to on headphones in the way you'd listen to a song. This isn't dishonest and it isn't decoration, at least not when scientists do it carefully. And the ones producing these releases generally are careful, publishing exactly what was measured, exactly how it was transformed, and exactly what the resulting pitch or rhythm actually represents. But it is a fundamentally different category of sound than a Mars microphone catching real wind or a Titan probe recording real atmosphere rushing past its casing. One is sound in the strict physical sense, pressure waves, air, a medium doing what mediums do. The other is data given a voice it never naturally had, real, meaningful, scientifically grounded, but built rather than captured. That distinction is the hinge this entire story turns on, and it's the distinction almost nobody makes when a black hole, sound, goes viral online, racking up millions of views with a caption that simply says NASA recorded this. Nothing was recorded. Something was measured and then it was translated. Carefully and specifically into a form your ears can process, and the story of how that happened, starting with a spacecraft launched in 1977 and still decades later sending data back from the edge of the solar system, is where we're headed next. Let's define the word properly, because from here on, almost everything we listen to depends on understanding exactly what it means. Sonification is the process of taking data, any data from any source measured by any instrument, and mapping it onto sound so that changes in the data become changes in pitch, rhythm, volume, or tone. That's the entire definition. Nothing in it requires the original data to have anything to do with sound in the first place. You've probably experienced a crude version of sonification without ever hearing the word. A Geiger counter clicks faster as radiation increases. That's sonification, radiation levels mapped onto rhythm. A heart rate monitor beeps in time with a pulse. That's sonification too. Electrical activity in a heart mapped onto a tone your ear can track without needing to watch a screen. Neither of these devices is a microphone. Neither one is recording a sound that already existed in the world. Both of them are taking a measurement, something that was never acoustic to begin with, and giving it an audible form. Because sound turns out to be an extremely efficient way for a human brain to track a changing pattern over time, often more efficient than a glance at a graph. Astronomy, in particular, has quietly leaned on this idea for far longer than most people assume. Radio astronomers have used simple sonification as a working diagnostic for decades, piping a raw signal through a speaker while scanning a sky survey, because an unexpected click, hum, or burst can sometimes register faster through an ear than through a printed chart. It's a modest, practical habit, not a discovery tool in itself, but it illustrates the same underlying principle. Sound is often a faster way for a trained observer to notice that something in the data has changed. Space science adopted this idea for a very practical reason, long before it became a public outreach tool. Astronomical data is enormous, and human eyes are good at scanning images, but not always good at spotting subtle patterns buried inside massive datasets, a slight rhythm in a light curve. A periodic dip in a radio signal, a pattern that repeats every few seconds inside months of recorded static. Turn that dataset into sound, and suddenly a trained ear can catch a rhythm that a trained eye might scroll straight past on a screen. Sonification, in other words, didn't start as a way to make space sound cool. It started as a research tool, and it's still used that way today, quietly, inside observatories and universities, long before any of it reaches a public audio release. The public-facing sonifications, the ones that rack up millions of views, the ones we'll spend most of the rest of this video on, are a direct descendant of that research tool, adapted for an audience rather than a lab. The measurement comes first, a real physical quantity captured by a real instrument, whether that's an X-ray brightness value, a radio wave amplitude, a magnetic field strength, or the density of charged particles drifting past a spacecraft. Then comes the mapping, a decision made deliberately by scientists about how that quantity should correspond to something audible, usually pitch, since pitch is the dimension of sound the human ear tracks most naturally. Higher measurement, higher note. Lower measurement, lower note. Sometimes it's more complex than that, multiple data streams mapped onto multiple instruments, like a small orchestra where each section represents a different wavelength or a different sensor. But underneath any amount of complexity, the core logic stays the same, a number that changed over time, translated into a sound that changes the same way. None of this makes the result any less real, in the sense that matters. A sonification of a black hole isn't a fabrication, an approximation dressed up as data, or an artistic liberty taken with something scientists don't actually understand. Every public sonification released by an institution like NASA comes with a technical explanation of exactly what was measured and exactly how it was converted. The mapping is published, the source data is public, and any scientist could, in principle, reconstruct the same audio from the same numbers. What makes it different from a Mars wind recording isn't honesty, it's category. One is air, moving, captured directly. The other is meaning, translated, built specifically so a human ear could access it. Keeping that distinction sharp, chapter after chapter, is the difference between understanding these recordings and simply being impressed by them, and it's the exact distinction almost every viral clip online quietly erases. It also helps to notice how wide a net this technique actually casts once you start looking for it, because black holes are far from the only target. NASA's Universe of Learning program, working with the Chandra X-ray Observatory, has sonified entire galaxies, translating X-ray optical and radio images into overlapping layers of sound, each wavelength assigned its own instrument, its own register, its own texture. A kind of orchestral score built directly from a telescope's raw data rather than composed by ear. Seismologists do something structurally identical on Earth, speeding up the low-frequency rumble of a real earthquake until it becomes audible, letting researchers listen for subtle features in a fault rupture that might not stand out clearly on a seismograph's printed trace. Even something as ordinary as a star's light curve, the graph of its brightness rising and falling over time as astronomers hunt for orbiting planets, has been sonified for research and outreach alike, each dip in brightness becoming an audible dip in pitch-turning months of quiet. Patient measurement into something you can listen to in under a minute. With that established, we can go looking for the first sonification most people never realize is one at all, a signal that came from further away than anything a human-made object has ever traveled. Sent back not as a curiosity, but as scientific proof of something extraordinary, that a spacecraft launched during the presidency of Gerald Ford had finally decades later left the solar system behind entirely. Voyager 1 launched in September 1977 on a mission originally planned to last around 4 years, built to fly past Jupiter and Saturn and send back the first close-up photographs of both. It did that job brilliantly within its first few years of flight, and then it kept going, propelled by the same physics that had gotten it there in the first place, with nothing in interplanetary space substantial enough to slow it down. Decades later, having long since finished its planned mission, Voyager 1 was still flying, still transmitting, moving further from the sun than any human-made object ever had. Somewhere out there, scientists knew, was a boundary, the edge of the heliosphere, the vast bubble carved out by the sun's own solar wind, the charged particles the sun constantly throws outward in every direction. Inside that bubble is, in a meaningful sense, still home, still dominated by our star's influence, its magnetic field, its particles. Outside it lies the interstellar medium, the thin, cold material that fills the space between stars, shaped not by our sun, but by the collective history of every star that has ever lived and died nearby. Nobody had ever measured that boundary directly. Nobody knew exactly how far away it was, or what crossing it would even look like from inside a spacecraft. The only way to find out was to wait for something to actually get there. Voyager 1's plasma wave science instrument, led by Don Gurnett at the University of Iowa, wasn't built to detect sound. It was built to detect plasma oscillations, vibrations among the electrons in the ionized gas surrounding the spacecraft, a completely different physical phenomenon from air pressure, even though both happen to produce a signal that oscillates over time. For years, that instrument mostly sat quiet, waiting for something to disturb the plasma enough to register. We were in a long, dry spell, Gurnett later said. The last time we detected a plasma oscillation was 9 years ago. Then, in October and November of 2012, and again in April and May of 2013, something changed. A massive eruption from the sun, a coronal mass ejection, a burst of charged material thrown outward by our star roughly a year earlier, finally reached Voyager 1's position and rattled the plasma around it, producing exactly the kind of oscillation the instrument was built to catch. Because of the enormous distance involved, and because Voyager's data was stored on old-fashioned tape and only transmitted back to Earth every few months, it took until the summer of 2013 for the relevant readings to actually land on Gurnett's desk. When they did, the pattern was unmistakable. Inside the heliosphere, plasma oscillations had always registered at a relatively low pitch, somewhere around 300 Hz, consistent with the thinner, sparser plasma of the solar wind, still under our sun's influence. But this new data was different. The oscillations Gurnett was looking at now sat between 2,000 and 3,000 Hz, a noticeably higher pitch, and one that corresponded, according to the physics of plasma waves, to a much denser surrounding medium. Denser plasma produces a higher frequency oscillation, sparser plasma produces a lower one. The jump from 300 Hz to nearly 3,000 Hz wasn't a curiosity. It was a measurement, and it pointed to one conclusion. Voyager 1 was no longer surrounded by the thin solar wind of the heliosphere. It had entered the denser interstellar medium. It had left the solar system. At a NASA press conference in September 2013, Gurnett played that data aloud for the room, converted into audible tones exactly the way a radio signal or an X-ray brightness map would be converted, pitch corresponding directly to frequency, frequency corresponding directly to plasma density. He called it the sounds of interstellar space, and in the framing that matters most, he was right too. Nothing about air, nothing about a microphone, nothing about pressure waves moving through any kind of atmosphere. Voyager 1 was, and remains, surrounded by conditions about as far from breathable air as anything measurable gets. But the plasma really was oscillating. The oscillation really was faster outside the heliosphere than inside it, and that change in frequency really did carry the meaning Gurnett assigned to it: solid physical. Peer-reviewed evidence, published later that year in the journal Science, that a spacecraft built during a decade when disco was still popular had, after 36 years of flight, finally crossed into interstellar space. The finding didn't stand alone for long. Voyager 1 has a twin, Voyager 2, launched just weeks earlier in 1977 on a different trajectory that carried it past Uranus and Neptune before it, too, began drifting toward the edge of the solar system. 6 years after Voyager 1's crossing, in November 2018, Voyager 2's own instruments registered the same signature, a jump in plasma density, confirmed independently, along a completely different exit path out of the heliosphere, having two separate spacecraft leaving through two separate regions of the boundary. Both reporting the same kind of transition gave scientists something a single data point never could: confirmation that what Voyager 1 detected in 2013 wasn't a fluke of geometry or a one-off anomaly, but a genuine consistent structure surrounding the entire solar system. It's worth being precise about what this recording is and isn't, because it sits at almost the exact midpoint of the spectrum we outlined back in Chapter 5. It isn't wind, recorded by a microphone, the way Insight or Huygens captured real sound moving through real air. But it also isn't a pure aesthetic translation of something scientists picked more or less arbitrarily to sound dramatic. The plasma really did oscillate at a real, measurable frequency, in a range that happens to fall inside human hearing almost by coincidence. No pitch shifting was even required to make Gurnett's press conference audio audible, only amplification and playback through a loudspeaker. It's a case where the universe, briefly and by chance, produced a signal already sitting inside the narrow band our ears can process, and scientists simply had to point a speaker at the data rather than transform it dramatically to get there. There's a strange irony buried in all of this, worth pausing on before we move to Saturn. Voyager 1 carries something else bolted to its side that has nothing to do with plasma waves or scientific instruments at all: the golden record, a phonograph disc loaded with genuine real acoustic sound from Earth, birdsong, ocean, waves, human laughter, greetings spoken in dozens of languages, 90 minutes of music ranging from Bach to Chuck Berry. That record contains actual recorded sound, captured by actual microphones, the same category of audio as the Mars and Titan recordings from Part 1. It was never meant to be played remotely, never transmitted back to Earth. It's a physical artifact, riding along in case someday something out there finds it and knows how to build a turntable. Meanwhile, the sound Voyager 1 actually sends back to Earth today, the sound scientists use, study, and occasionally release to the public, isn't acoustic at all. It's plasma data converted into tone. The spacecraft is, in a sense, carrying real sound outward while transmitting something else entirely back. Two completely different categories of sound of space, riding on the same 45-year-old spacecraft, meant for two completely different audiences that will likely never overlap. Both spacecraft are still out there, still working, still sending data back across a gap that keeps widening by the hour. Voyager 1 now sits more than 170 astronomical units from the Sun, over 170 times the distance between Earth and our own star, and every signal it sends now takes more than 23 hours to arrive, one way, traveling at the speed of light. Engineers at JPL have described the exchange in almost comic terms. Send a good morning on a Monday, and the reply doesn't arrive until Wednesday. By the time you finish this sentence, the spacecraft has moved further away than it was when you started it. If Voyager's interstellar tones were a case of nature handing scientists something almost ready-made for human ears, Saturn's radio emissions are closer to the opposite. A signal so far outside the audible range that turning it into sound required a deliberate substantial shift, and produced. Almost as a side effect, one of the eeriest sounds of space ever released to the public. Saturn, like Earth and Jupiter, generates its own natural radio emissions, tied directly to its orrery, the northern and southern lights that form when charged particles spiral down along the planet's magnetic field lines near its poles. Earth produces a version of this too, called auroral kilometric radiation. Generated by the same basic physics above our own poles, though far too faint and far too easily blocked by our atmosphere for anyone to build a public sound of Earth's aurora, recording the way scientists eventually would for Saturn. Jupiter, with by far the strongest magnetic field of any planet in the solar system, produces its own booming version of the same phenomenon, first picked up by radio telescopes on Earth decades before any spacecraft ever visited. Saturn's version, known formally as Saturn kilometric radiation, had first been detected by the twin Voyager spacecraft during their brief flybys in 1980 and 1981, but Voyager only passed through the system once, gathering a narrow snapshot before continuing outward. Cassini, which entered orbit around Saturn in mid-2004 and stayed for the next 13 years, becoming the first spacecraft ever to orbit the planet rather than simply fly past it, had something no flyby mission ever could: time. Time to watch the radio emissions shift, day after day, season after season, as Saturn's magnetic environment shifted with it, all the way through to the mission's dramatic conclusion in 2017, when controllers deliberately plunged the spacecraft into Saturn's atmosphere to protect its potentially habitable moons from contamination. Cassini's radio and plasma wave science instrument, built, like Voyager's plasma wave detector, under Don Gurnit's direction at the University of Iowa, recorded these emissions continuously, at a resolution far higher than anything Voyager's brief flyby had managed. The radio waves themselves oscillate at frequencies far above anything a human ear could ever process: electromagnetic radiation, not sound, moving at a pace measured in kilohertz to megahertz, well beyond audible range even before you consider that it isn't acoustic in the first place. To make it audible at all, Cassini's science team shifted the frequencies dramatically downward, compressing a wide, fast-moving radio spectrum into the narrow window of pitches a person can actually hear. What came out the other side, according to Bill Kurth and Don Gurnit? The University of Iowa researchers who published the findings in 2005 sounded less like music and more like something out of a haunted house, bursts and swells that one team compared only half-jokingly to a Halloween sound effects reel. Later researchers, listening to the same kind of data, described it as resembling a spinning air raid siren, rising and falling in intensity with each rotation of the planet, the pitch and pattern shifting as Cassini's position relative to Saturn's magnetic poles changed over the course of the mission. Nobody built that siren sound intentionally. Nobody designed Saturn's magnetic field to produce something dramatic for a documentary soundtrack. The pattern simply exists in the data tiny radio sources Kurth and Gernot proposed, moving up and down along Saturn's magnetic field lines, each shift showing up as a shift in the translated pitch. That detail matters because it's easy to hear something this theatrical and assume scientists exaggerated it for effect. They didn't need to. The rotation, the rising and falling swells, the harsh, layered texture, every part of that comes directly from real variation in a real magnetic environment, a genuine physical structure high above Saturn's clouds, simply moved down into a register your ears can process. Nothing was invented. Only the pitch was moved, and moved by an enormous amount, since we're talking about shifting emissions from well above the radio spectrum down into the same narrow band your voice occupies when you speak. There's a practical reason scientists went to this trouble beyond simple curiosity, and it connects back to the same logic that first justified sonification as a research tool in Chapter 5. Saturn's kilometric radiation doesn't just switch on and off. Its pitch rises and falls, its texture thickens and thins, in patterns tied to the planet's rotation and to the state of its magnetosphere at any given moment. Early researchers had hoped that regular changes in this radiation, much like a lighthouse beam sweeping past an observer once per rotation, might act as a clock, letting scientists measure Saturn's true rotation, rate the way similar patterns had worked at Jupiter. Saturn turned out to be far messier than that. Cassini found that the radio signal wasn't behaving like a single steady beat at all. The northern and southern hemispheres were pulsing at two slightly different rates, one closer to 10 hours and the other closer to 10. And around the planet's 2009 equinox, those two rates began drifting toward each other before crossing over entirely, the hemispheres effectively swapping tempo. Scientists don't think Saturn's interior is physically rotating at two different speeds. The leading explanation points instead to high-altitude winds shaping the emission rather than the planet's core. Either way, hearing the data continuously over years, rather than during one brief flyby, is what made a mystery like that visible in the first place. Compare Saturn's siren to Voyager's interstellar tones for a moment, because the contrast is the whole point of this chapter. Voyager's plasma oscillations needed almost no adjustment, a happy coincidence of physics landing a real signal close to audible range already. Saturn's kilometric radiation needed a massive, deliberate frequency shift to become audible at all, moving a signal from a part of the electromagnetic spectrum with no natural relationship to sound whatsoever. Both get called the sound of space. Both are legitimate, careful, scientifically grounded translations of something real. And both are worlds apart from the recordings. We spent part 1 listening to Wind on Mars, atmosphere rushing past a probe on Titan, where a microphone did nothing more exotic than its job. Look at what we've covered so far, laid end to end, and a pattern starts to emerge, a sliding scale, running from genuinely acoustic all the way to entirely translated, with every stop along the way still honestly earning the word sound. At one end, Mars and Titan, where real atmospheres carried real pressure waves, picked up by real microphones, needing nothing more than a pitch adjustment to become audible, the same category of recording as any sound captured on Earth. One step further out, Voyager 1, surrounded by plasma rather than air, detecting oscillations that happened, almost by chance, to fall near the edge of human hearing already, requiring barely any transformation to reach a loudspeaker. One step further still, Saturn's kilometric radiation, a genuine radio signal generated by a genuine magnetic environment, shifted dramatically downward in pitch to become audible at all, real data, real structure, but no longer anything close to what a microphone would ever have picked up on its own. It's worth noticing something else about this progression, too, something that isn't obvious until you see all three cases side by side. Each of these recordings, however different in origin, tells scientists something they couldn't easily learn any other way. Mars's wind sounds carried information about atmospheric turbulence at the surface. Titan's descent audio hinted at atmospheric thickness and texture, layered into the noise itself. Voyager's tones didn't just prove a spacecraft had crossed a boundary. They let scientists calculate, from the frequency alone, the density of the interstellar medium surrounding it, a measurement that would have been extraordinarily difficult to make any other way at that distance. Saturn's shifting radio periods exposed an unsolved mystery about high-altitude winds that nobody had anticipated before Cassini settled into a long-term orbit. None of these sounds of space exist purely for spectacle. Every one of them, translated or not, carried real scientific weight, which is exactly why space agencies keep producing them, release after release, even though a purely decorative version would arguably be easier and cheaper to make. Each step outward has taken us further from air, further from anything resembling a traditional recording, and further into territory where the word sound survives only because scientists chose, deliberately and transparently, to build it a way in. And there's one more step left to take, the largest one yet, by an almost unimaginable margin. Somewhere out past every planet, every moon, every boundary of our own solar system, sits an object whose voice, once translated, needed to be shifted not by a few octaves. Not by a dramatic downward sweep like Saturn's, but by a factor so large that scientists measure it in the hundreds of trillions. Here's a way to picture just how large that gap really is before we cross it. Saturn's radio emissions needed to be shifted down by a few orders of magnitude, dramatic, but still within a range you could describe in ordinary terms, moving a signal from the radio portion of the spectrum into the audible range a few steps below it. What we're about to encounter isn't a signal from the radio portion of the spectrum at all. It's a signal from deep within the X-ray portion, energy so far above visible light, let alone sound, that comparing the two scales is almost meaningless without the specific number involved. And the environment producing that signal isn't a planet's magnetic field, shaped by aurory and solar wind. It's the churning superheated gas surrounding one of the most extreme objects the universe produces at all, a supermassive black hole. Sitting at the exact center of a cluster, containing hundreds of individual galaxies, discovered by pure accident by scientists who weren't looking for anything resembling a sound in the first place. That object sits at the center of a galaxy cluster 240 million light-years from Earth, and the signal it produces has nothing to do with radio waves or plasma or magnetic fields. It comes from X-rays, the same category of radiation doctors use to photograph bone, moving through gas hot enough to strip electrons from atoms outright, hot enough to be measured not in degrees, but in the tens of millions. And somewhere inside that furnace of gas, astronomers found something they weren't expecting at all, a note, a single, sustained, impossibly deep note produced by a black hole, discovered by accident, and eventually turned into the most listened to sound of space NASA has ever released. We're going to spend real time with that discovery because it deserves it, not just the sound itself, but the 2 decades of science that led up to it, the accident that first revealed it in 2003. And the reason a note pitched 57 octaves below middle C turns out to matter for understanding how galaxy clusters, some of the largest gravitationally bound structures in the entire universe, hold themselves together in the first place. That's where we're going next, and it's the point in this story where the sounds of space stops being a curiosity and starts being genuinely strange. In 2002, a team of astronomers pointed the Chandra X-ray Observatory at the Perseus cluster for what would eventually add up to more than 2 full days of observing time, an enormous investment for a single target, even by the standards of a space telescope. They weren't hunting for sound. Nobody on the team went into that observation expecting to find anything remotely like it. What they were actually studying was far more mundane, at least on paper. The hot gas that fills the space between the hundreds of galaxies inside the cluster, and the puzzling question of why that gas wasn't cooling down the way basic physics said it should. Chandra itself is worth a brief introduction, since almost everything in this final stretch of the video depends on it. Launched by NASA in 1999, it's an X-ray telescope. Built to see a part of the electromagnetic spectrum blocked almost entirely by Earth's atmosphere, which is exactly why it had to go to space in the first place, rather than sitting in an observatory on a mountaintop, the way an optical telescope might. X-rays are produced by matter that's extraordinarily hot or extraordinarily energetic, the multi-million-degree gas inside galaxy clusters, materials spiraling into black holes, the aftermath of supernova explosions. Chandra doesn't just detect that X-ray light, it resolves fine structure within it, sharp enough to pick out subtle brightness variations across a cluster hundreds of millions of light-years away, which turned out to be exactly the capability needed to notice something as faint as a ripple. Galaxy clusters like Perseus aren't just collections of galaxies floating near each other. They're bound together by gravity into some of the largest structures in the observable universe, and the space between the individual galaxies isn't empty. It's filled with gas superheated to tens of millions of degrees. Glowing brightly enough in X-rays that Chandra could photograph its structure in detail for the first time. That gas should, by every straightforward calculation, have been cooling steadily, losing energy as it radiated X-rays outward, gradually collapsing inward as it did. It wasn't. Something was pumping heat back into the cluster gas fast enough to counteract that cooling, and astronomers had a strong suspicion about what. The supermassive black hole sitting at the very center of the cluster's largest galaxy, NGC 1275. What Chandra's deep image revealed, when the team led by Andrew Fabian at Cambridge's Institute of Astronomy finally examined it closely, wasn't a single dramatic burst or a smoking gun in the traditional sense. It was something subtler, faint, concentric ripples spreading outward through the X-ray bright gas, like rings expanding across a pond after a stone breaks the surface, except stretched across distances of tens of thousands of light years. The ripples themselves seem to trace back to 2 vast cavities in the gas, carved out by jets of material blasting outward from the black hole's immediate surroundings. Each time the black hole's activity inflated a new bubble in the surrounding gas. It appeared to send a pressure wave rippling outward through the cluster, the same basic physics as a ripple crossing a pond or a shockwave crossing the air after a clap of thunder. Just playing out across a medium hundreds of thousands of times larger and hotter than anything on Earth. That last detail is the one that matters most for this story. A pressure wave expanding outward through a medium, disturbing that medium as it travels, that's not a metaphor for sound. That's the literal textbook definition of it. And unlike almost everything covered in Part 2, where scientists had to reach for data with no acoustic relationship to what they were measuring, the ripples in Perseus's gas were exactly the physical process a sound wave is. Fabian and his team didn't need to translate some unrelated signal into an artificial tone, the way Saturn's radio emissions required. They needed only to calculate the pitch a wave like this would actually produce, given its measured wavelength and the physical properties of the gas it was moving through, and when they did the math, the result was almost absurd in its precision. In musical terms, the note came out to B-flat, specifically a B-flat some 57 octaves below middle C, oscillating with a period of roughly 10 million years between each cycle, a single wave taking longer to complete than most species on Earth have existed. It's worth understanding, at least roughly, how a black hole produces something like this in the first place, because the mechanism turns out to be almost mechanical in its simplicity, however exotic the object generating it. Supermassive black holes at the centers of active galaxies don't just sit still, quietly consuming matter that falls toward them. Material spiraling inward heats up dramatically before it crosses the event horizon, and a fraction of that energy gets redirected outward instead, launched as powerful jets of particles moving at close to the speed of light, blasting away from the black hole's poles. Where those jets slam into the surrounding gas, they don't just pass through it, they push it aside, carving out enormous cavities, low-density bubbles sometimes tens of thousands of light-years across, visible in Chandra's X-ray images as dark voids surrounded by brighter, denser gas. Each time a new bubble inflates, it shoves against the gas around it, and that shove propagates outward as a pressure wave. A sound wave in the strictest sense generated the same basic way a slamming door generates one. Just on a scale where the door is an exploding cavity of hot gas the size of a small galaxy. Fabian summarized the discovery simply, in a line that ended up quoted in nearly every article written about it since. Astronomers had already observed the light and heat produced by black holes. Now, for the first time, they had detected the sound. At a frequency more than 1,000,000 billion times below the lower limit of human hearing, it stood, at the time, as the deepest note ever measured from any object in the universe. Nobody built that note deliberately. Nobody chose B-flat because it sounded dramatic. The physics of a supermassive black hole inflating bubbles in superheated gas simply produced it, and Chandra's instruments happened to be sensitive enough, and the observation deep enough to catch it. The 2003 discovery was a measurement published in scientific papers, discussed at conferences, understood in detail by a small community of astrophysicists, but it wasn't in itself something the public could press play on. That came almost 2 decades later in May 2022 when NASA's Universe of Learning program, working again with Chandra data, released a direct sonification of the Perseus black hole's sound waves for the first time. Not a musical reinterpretation, not an artistic impression, but the actual ripple pattern Fabian's team had identified back in 2003. Extracted from the X-ray data and resynthesized into a range human ears could process. The scaling involved is difficult to describe without sounding like an exaggeration, so it's worth being precise. The original pressure wave oscillates roughly 57 to 58 octaves below the range of human hearing. To make it audible at all, the Chandra team's sonification tools scaled the signal upward by that same 57 to 58 octaves, which works out to raising the frequency by a factor of somewhere between 144 quadrillion and 288 quadrillion. A quadrillion is 1,000,000 billion, 288 quadrillion is 288 followed by 15 zeros. There's no everyday comparison that makes a number like that intuitive. It's not a lot louder or a lot higher. It's a transformation on a scale that has no real analog anywhere else in ordinary experience. and yet on the other end of that transformation, what comes out is unmistakably a sound, a low, resonant, pulsing tone. Closer to a foghorn or a distant moan than to anything mechanical moving outward from the center of the visualized image, exactly as the real pressure wave once moved outward through the cluster's gas. NASA released a second sonification alongside Perseus's, built from an entirely different black hole and an entirely different technique, and comparing the two says almost as much about this whole subject as either one does on its own. The second target was M87, a galaxy roughly 55 million light-years away. Home to the first black hole ever directly imaged, a result that on its own had already made headlines around the world in April 2019, when the Event Horizon Telescope, a network of radio observatories spanning the globe, combined years of data to produce a single glowing ring of light bent around a shadow, the silhouette of the black hole itself cast against the superheated material swirling just outside its event horizon. That image measured the black hole's mass directly at roughly 6 billion times the mass of the Sun, and Chandra contributed its own coordinated observations at the time, tracking the vast, multi-million-degree halo of X-ray bright gas surrounding the galaxy from a much wider field of view than the Event Horizon Telescope's narrow, close-up image could capture alone. Where the Perseus sonification translated one specific physical phenomenon, a real pressure wave in real gas, the M87 sonification worked differently, built from a composite image that layered together data from 3 separate telescopes: X-ray light from Chandra, visible light from Hubble, and radio waves from the Atacama Large Millimeter Array in Chile. Rather than tracking one pressure wave rippling outward, this sonification scanned the layered image from left to right, converting each point into a tone, with radio data mapped to the lowest pitches visible light to the middle range, and X-ray data to the highest tones, all playing together as the scan swept across. The result sounds nothing like Perseus's low, resonant pulse, where Perseus registers as something closer to a single sustained breathing tone. M87's sonification comes across as brighter, busier, closer to ambient music with scattered chimes than to a foghorn, not because M87's black hole is somehow less extreme. If anything, it's the more massive of the two at roughly 6 billion times the mass of the Sun compared to NGC 1275's estimated 800 million, but because the two sonifications are measuring and mapping completely different things, Perseus is a translation of one specific physical wave. M87 is a translation of an entire multi-wavelength portrait, scanned into sound the way a photograph might be scanned into a fax machine, one line at a time. Both get filed under the same simple headline, the sound of a black hole, and both are legitimate, carefully documented translations of real data. But even within that single category, sonification, there's enormous room for different choices, different techniques, and dramatically different results. It's worth pausing here and placing Perseus precisely on the spectrum we built across Part 2, because it doesn't sit where you might expect. Saturn's kilometric radiation was a genuine physical signal, but one built from radio waves, electromagnetic radiation with no natural connection to sound, requiring a dramatic, engineered shift to become audible. Voyager's plasma tones were closer to real sound, in the sense that they were oscillations in a physical medium, but that medium was thin, ionized plasma, about as far from breathable air as anything gets. Perseus is different from both, and in a way that makes it the strangest case of all, precisely because it's the most literal. The gas filling the Perseus cluster is real. It's not a mathematical abstraction. And it's not a stand-in for some other kind of measurement. It's an actual medium hundreds of thousands of light years across, dense enough and hot enough to carry an actual pressure wave the exact same way Earth's atmosphere carries the sound of a voice. Just unfathomably larger and unfathomably slower. When the black hole at the center of NGC 1275 inflated those cavities in the surrounding gas, it generated a genuine sound wave in the strictest physical sense of the term, the same basic phenomenon as a cymbal crash or a slamming door. Expanding outward through a medium exactly the way sound is defined to behave. Nothing about that description involves translation, mapping, or artistic interpretation. The wave existed on its own, independent of anyone choosing to listen to it, the same way a tree falling in a forest still displaces air whether or not anyone is there to hear it land. There's an odd visual irony buried in all of this, too. On Earth, sound and light travel through the same air, but only one of them is visible to your eyes. You can watch a drum being struck, but you can't see the sound wave itself moving outward from it. Inside the Perseus cluster, that relationship flips entirely. The gas is hot enough and glowing brightly enough in X-rays that the pressure wave rippling through it actually shows up as a visible brightness variation in Chandra's images. Astronomers can see the sound wave directly mapped out as a faint ring of slightly denser, slightly brighter gas. Expanding outward exactly the way ripples spread across a pond after a stone breaks the surface. Nobody can watch air move the way sound moves through your living room. Astronomers, remarkably, can watch a black hole's sound wave move through a galaxy cluster, precisely because the medium it travels through happens to glow. What required translation wasn't the existence of the sound, it was making it audible. A wave oscillating once every 10 million years is, for all practical human purposes, frozen. No ear, no matter how sensitive, no matter how much time it had, could ever perceive a single cycle of it directly, because a human lifetime isn't remotely long enough to experience even one full oscillation. That's an entirely different problem from the one Saturn's radio waves presented. Saturn's signal was outside human hearing because it moved too fast electromagnetic radiation, oscillating millions of times each second, needing to be slowed down into audible range. Perseus's signal is outside human hearing because it moves unimaginably slower than anything audible, a wave so patient it makes plate tectonics look frantic by comparison, needing to be sped up, not slowed down. And sped up by a margin so extreme that ordinary units stop being useful at all. There's a further wrinkle worth naming here, because it separates Perseus even from Mars and Titan, the two cases from Part 1 that come closest to it in spirit. When InSight caught Martian wind, or when Huygens recorded Titan's atmosphere rushing past its casing, both signals fell reasonably close to the range human ears already cover, thin, low, and quiet, but fundamentally within reach, needing only a modest pitch adjustment measured in single octaves to become clearly audible. Perseus's wave sits 57 octaves outside that range, a gap so large that no gradual nudge could ever close it. There's no equivalent anywhere else in this video for a signal this real and this far from perceptible at the same time, genuinely physical. Genuinely a sound wave in the strictest sense, and yet more distant from human hearing than any translated radio signal or plasma oscillation covered so far. This is, in the end, the detail almost every viral clip online quietly leaves out, and it's the detail this entire video has been building toward since Part 1. NASA recorded the sound of a black hole isn't quite right, and it isn't quite wrong either. Nothing was recorded in the sense a microphone records anything. There was no instrument capable of directly capturing a wave that slow, over a timescale that vast. But the sound itself, unlike Saturn's radio hiss or Voyager's plasma oscillations, was never manufactured or assigned. It already existed, precisely as real as the wind that InSight caught on Mars or the atmosphere hygiens recorded above Titan, just operating on a timescale and at a pitch that human perception was never built to reach. It would be easy to end the story here, treating the note itself as the finish line, an extraordinary, almost unbelievable fact filed away and moved past. But the reason astronomers spent 2 decades studying this sound, rather than simply marveling at it once and moving on, is that it answers a question that has nothing to do with music and everything to do with how galaxy clusters survive at all. Go back to the puzzle that sent Fabian's team looking at Perseus in the first place. The cluster's gas should have been cooling, and it wasn't. Hot gas radiates energy away as X-rays, loses heat, and left alone, should eventually cool enough to collapse inward, feeding a wave of new star formation as it falls toward the cluster's center. Astronomers had been watching for exactly that kind of collapse in clusters like Perseus for years, and it consistently failed to show up in anything like the quantities the physics predicted. Something had to be replacing the lost heat continuously, gently, and on a scale large enough to keep an entire galaxy cluster from cooling down. This puzzle has a name in the astrophysics literature, the cooling flow problem, and it's not a minor footnote. Clusters like Perseus are among the largest gravitationally bound structures the universe has ever assembled, and the hot gas filling them accounts for far more ordinary matter than every star in every galaxy inside the cluster combined. Understanding what keeps that gas from cooling isn't just a detail about one particular cluster's temperature. It's a question that touches on how galaxies form, how star formation is regulated across the universe, and why the largest structures in the cosmos look the way they do rather than collapsing far more dramatically than they actually do. A black hole quietly heating its surroundings through sound, rather than through some more violent, more obviously destructive process, turned out to be a far more elegant answer than anyone initially expected. The sound waves rippling outward from the central black hole turned out to be a serious candidate for exactly that mechanism. Each pulse of jet activity, each new bubble inflated in the surrounding gas sends a wave of pressure outward, and as that wave travels however slowly, it carries energy with it, gradually depositing heat into the gas. It passes through the same basic principle by which any sound wave loses energy to the medium it moves through over distance. Multiply that process across millions of years, thousands of cycles, and a black hole quietly, repeatedly inflating and releasing pressure into its surroundings, starts to look less like a violent event and more like something closer to a very slow, very patient heater, one that may be the missing piece keeping the hot gas in clusters like Perseus from ever fully cooling down. Researchers have calculated that the sound waves detected in Perseus carry enough energy to meaningfully offset a significant share of the cluster's radiative cooling, though the exact balance, and how efficiently that sound energy actually converts into heat as it travels, remains an active area of study rather than a fully settled number. It's worth being honest about where the science stands today rather than overselling it. This isn't a fully closed case, wrapped up neatly in a single 2003 discovery. Subsequent, even deeper observations of Perseus, hundreds of additional hours of Chandra time collected in the years after the original finding, refine the picture considerably. Measuring the ripples with enough precision to calculate roughly how much energy they carry, and how that energy declines the further the waves travel from the black hole. Similar ripple patterns have since turned up in other galaxy clusters too, suggesting Perseus isn't a strange one-off, but an example of something that may happen routinely, wherever a supermassive black hole sits at the center of enough surrounding gas. What remains genuinely open is the fine detail, exactly how efficiently a slow-moving pressure wave converts into heat as it crosses hundreds of thousands of light years, and whether sound waves alone are enough to explain the full scale of the heating. Or whether they work alongside other mechanisms astronomers are still untangling. That's worth sitting with for a moment, because it reframes everything covered in this video so far. This isn't a case of scientists translating data into sound purely to make it accessible to a general audience, though that translation did eventually happen in 2022 for exactly that reason. The sound itself, independent of anyone choosing to listen to it, may be doing real physical work, holding one of the largest gravitationally bound structures in the universe together in a way gravity alone can't fully explain. Somewhere out past every planet, every moon, every recording a microphone could ever pick up, there's a black hole quietly humming a single impossibly deep note, and that note might be one of the reasons its entire galaxy cluster hasn't already collapsed. It also reframes what the sounds of space has actually meant. Across every chapter of this video so far, Wind on Mars told scientists about surface turbulence, Titan's descent audio hinted at atmospheric texture, Voyager's tones measured the density of the space between stars. Saturn's shifting radio periods exposed a genuine mystery about high-altitude winds. And now, at the far end of the spectrum, a black hole's sound wave may be quietly regulating the temperature of one of the largest structures the universe has ever built. None of these recordings exist because scientists wanted something interesting to release to the public first and found the science second. Every one of them started as a real measurement, taken to answer a real question, that only later became something the rest of us could actually sit down and listen to. Here is the number, stated plainly, the way it deserves to be stated after everything that's led up to it. To make the sound from the Perseus black hole audible to a human ear, scientists raised its pitch by a factor of up to 288 quadrillion. Sit with that figure for a moment, because every other transformation covered in this video looks almost modest by comparison. Mars's wind needed a shift of 2 octaves. Saturn's radio emissions needed a shift dramatic enough to move a signal out of the radio spectrum entirely, but still expressible in ordinary terms, a few orders of magnitude at most. Perseus needed 57 to 58 octaves, not 2, not a dozen. But nearly 60 successive doublings of pitch, each octave doubling the frequency of the one, before it stacked on top of each other, until a wave that completes one single cycle every 10 million years finally lands somewhere a human ear can process it as a low resonant tone. 10 million years compressed into something you can hear in the length of a single breath. There's a way to make that scale slightly more concrete, though concrete is a generous word for a number this size. If you could somehow speed up the rotation of the Earth by that same factor, 288 quadrillion times, a single day would no longer last 24 hours. It would last a fraction of a second, faster than any process the human nervous system is capable of registering at all. Try another angle on the same number. A single human lifetime, generously measured at around 90 years, is roughly 110,000 times shorter than the black hole's 10 million year wave cycle. Stack more than 2,600 full human lifetimes end to end, one after another, and you'd still only be watching one single oscillation complete, a wave that began rippling outward through Perseus's gas long before anything resembling a human being existed to eventually build a telescope capable of noticing it. And even that staggering span barely begins to approach the scale of the number that mattered for turning it into sound. The gap between one oscillation every 10 million years and one oscillation you can hear right now isn't a gap measured in lifetimes or even in the age of a species. It's a gap that only makes sense expressed as a number with 15 zeros in it. That's the scale of transformation packed into the note NASA released in 2022, not a dramatic embellishment, not an artistic flourish, but the literal, documented distance between a wave that took 10 million years to complete one cycle and a tone your ear can recognize the instant it starts playing. And underneath all of that transformation, the physics never stopped being real. The wave existed before anyone measured it, before anyone converted it, before anyone pressed play on a sonification 100 million light-years removed from its actual source. It rippled outward through hundreds of thousands of light-years of superheated gas, carrying real energy, doing real work, possibly holding an entire galaxy cluster's temperature in balance for millions of years at a stretch, all of it happening in total permanent silence. By any definition of silence, a human standing nearby could ever have perceived, even if standing nearby were remotely possible. It took a space telescope 53 hours of observing time, a team of astronomers willing to look closely enough to notice a ripple nobody expected. And a scaling factor with 15 digits in it, just to let anyone anywhere finally hear what had already been happening for longer than most species on Earth have existed. When NASA released the Perseus sonification in May 2022, it didn't quietly enter a scientific archive somewhere. It spread. Within days, the clip had been featured among the most viewed posts on Reddit, picked up by outlets around the world, and eventually reached more than 4 million listens and views across NASA's own media channels alone, a number that doesn't even count the millions of additional plays across the accounts that reposted it afterward. The clip proved popular enough that both the BBC and Netflix later requested it for use in separate documentaries about the universe, a level of crossover from research release to mainstream media that almost no other single piece of astronomical data has achieved. By any measure, it became one of the most successful pieces of public astronomy content ever released. And within roughly the same window of time, a second, quieter pattern started forming alongside it. Headlines, captions, and video titles describing the clip as something NASA had recorded, a black hole's actual voice, finally captured after decades of searching. That framing isn't a small error. It's the exact confusion this entire video has been built to untangle, and it's worth naming plainly why it keeps happening, video after video, platform after platform, even years after NASA's own scientists explained the process in careful detail alongside the original release. Part of it is simply how information moves online. A headline has to work in about 4 words, and NASA records black hole sound is a far more compelling 4 words than NASA converts X-ray pressure wave data into audible pitch using a 57-octave scaling factor. One of those headlines gets clicked, the other gets scrolled past. Nobody sits down and deliberately decides to mislead an audience about sonification. The shortening happens gradually, headline by headline, repost by repost, each version losing a little more of the technical nuance the previous one still had, until what's left is simply recorded, full stop, no asterisk. Part of it is also that the distinction genuinely is subtle, and subtlety doesn't survive well in a 15-second clip. Everything covered across the last 3 parts of this video, the difference between a Mars microphone and a Voyager plasma reading, between Saturn's radio hiss and a black hole's honest-to-physics pressure wave, took close to 2 hours to explain properly, with each case building on the one before it. A short-form video has 15 seconds, sometimes 30. There simply isn't room to draw the line between this is a real sound wave that needed pitch shifting, and this is a translated dataset with no acoustic history at all, in the space most platforms allow before a viewer swipes to the next thing. The nuance doesn't survive the format, not because anyone is lying, but because the format was never built to carry it. This is, in some sense, the entire argument for a format like this one existing at all. A 15-second clip can show you that a black hole has a sound. It cannot show you why that sound needed a factor of 288 quadrillion to become audible, why that number is different in kind from Saturn's radio shift or Mars's 2-octave adjustment, or why the distinction actually matters for understanding what you're hearing rather than just being impressed by it. Compressing a genuinely layered scientific story into a single dramatic clip isn't wrong, exactly. It's simply a different kind of object, built to circulate quickly rather than to explain thoroughly, and it was never going to carry the full weight of the science underneath it. Something has to hold the longer version, the version with room for InSight's unplanned wind and Titan's ordinary hiss and Voyager's decade-long silence before the signal finally came, and where the true weight of 288 quadrillion can be unpacked instead of just stated. That's the gap this kind of long-form document exists to fill, not competing with the 15-second clip, but supplying what it was never built to carry. And part of it, less charitably, is that NASA recorded a black hole screaming performs better than the accurate version, and performance is what most platforms are built to reward. A clip framed as an impossible recording, something that shouldn't exist, plays into exactly the kind of "this shouldn't be possible" hook that spreads fastest online, the same instinct this very video's cold open leaned on, because it's a genuinely effective way to earn someone's attention. The difference is what happens next. A responsible version of that hook resolves the tension honestly, the way we've tried to do across the last 3 parts. A less careful version simply leaves the audience believing something that isn't quite true, because resolving it honestly is less exciting than leaving the mystery intact. None of this makes NASA's original releases dishonest, quite the opposite. Every public sonification referenced in this video came bundled with a plain language technical explanation, published alongside the audio itself, describing exactly what was measured and exactly how the conversion worked. The 2022 Perseus release, for instance, went out of its way to note explicitly that the popular idea of total silence in space is itself a misconception worth correcting, and explain the 57 to 58 octave scaling in the same breath as the audio itself. The scientists involved were consistently careful, transparent, and precise. The distortion happens downstream, in the layers of reposting and recaptioning that strip that explanation away one repost at a time, until only the most exciting 4 words survive. That's not a NASA problem. It's a distribution problem, and it's exactly the kind of problem a longer, slower format like this one exists to correct, by giving the actual explanation the 2 hours it needs rather than the 15 seconds it gets everywhere else. There's a broader pattern worth naming here too, because black holes aren't the only place it shows up. Anytime a complex scientific result gets compressed for mass distribution, something gets lost, and the direction of that loss is rarely random. It almost always trends toward whatever version of the story is more dramatic, more definitive, or more shareable than the careful original. A sonification becomes a recording. A candidate mechanism that may explain part of the observed heating becomes the mystery is finally solved. A measurement consistent with becomes proof that none of these compressions are usually malicious. Most of them happen because someone genuinely excited about a discovery reached for the most vivid available language, without realizing how much weight that vividness was quietly removing from the actual science underneath it. Recognizing the pattern in one case, this one, black holes and their supposed voices, makes it considerably easier to spot the same pattern the next time it shows up somewhere else entirely, on a topic that has nothing to do with sound at all. Consider how easily the confusion compounds once it starts. A science outlet publishes a careful headline, "NASA sonifies the sound of a black hole's pressure waves." A second outlet, summarizing the first, simplifies it slightly, "NASA reveals the sound of a black hole." A short-form video, built from the second outlet's summary rather than the original, drops the remaining nuance entirely. NASA finally recorded a black hole, and it's terrifying. 3 steps, each individually a small simplification, and the entire scientific process. The 2003 discovery, the 2022 sonification, the specific, documented 57-octave scaling factor, has quietly disappeared, replaced by a single word, recorded, that was never accurate at any point along the chain. Nobody in that chain necessarily intended to mislead anyone. The distortion is cumulative, not deliberate, which is part of what makes it so difficult to correct once it's underway. The same compounding shows up, slightly differently, in how people talk about the Mars and Titan recordings from Part 1, cases where the word "recorded" is actually accurate, but where a different kind of distortion creeps in instead. Because InSight's wind and Huygens' atmosphere are real recordings, they sometimes get treated as proof that space actually sounds like this, as though a single gust of Martian wind or a few minutes of Titan haze somehow represents what space in general sounds like, everywhere, all the time. That's its own kind of overreach, just running in the opposite direction from the black hole confusion, not claiming a sonification is a recording, but treating one narrow specific recording as a stand-in for the vastly larger, vastly quieter reality of most of space, most of the time. Which really is close enough to silent that no instrument built so far has ever caught anything at all. Here's the test worth carrying forward. The next time a Sound of Space clip crosses your feed, ask what physically existed before anyone pressed play. If the answer is air or something like it, actually moving, Mars's wind, Titan's atmosphere, even Perseus's impossibly slow pressure wave, you're dealing with a real, if translated, sound. If the answer is a measurement of something that was never acoustic at all, a radio signal, an X-ray brightness map, a magnetic field reading, you're dealing with a sonification, legitimate, scientifically grounded, but a different category of thing entirely. Both are worth your attention. Neither deserves to be misrepresented as the other, and now, if nothing else, you have the tools to tell the difference yourself. It's worth adding one more layer to that test, because was it ever a real physical wave only answers half the question. The second half is, how much was that wave shifted to become audible, and does the shift change what the sound seems to communicate? A 2-octave adjustment, like InSight's Martian wind, barely alters the character of what you're hearing. It still sounds recognizably like wind, because it essentially still is. A 57-octave adjustment, like Perseus's black hole, produces something so far removed from the original signal's actual behavior that the resulting tone tells you almost nothing about what the wave, really, sounds like, because a wave that slow was never going to sound like anything to a human ear in any form. The translation is honest and scientifically valuable, but it's worth remembering that a black hole, singing, is a human-scale metaphor layered onto something that left alone would never have produced anything resembling music at all, just a pressure difference patiently rippling outward. over a timescale indifferent to whether anyone was ever going to notice. Before going any further, it's worth taking a moment to appreciate the full distance this video has actually traveled, because laid end to end, it's a stranger journey than any single chapter made it feel in the moment. It started with a claim nearly everyone has heard and nearly everyone accepts without examining closely: space is silent. And it is, mostly. Vacuum genuinely can't carry sound, and nothing about that basic physics changes no matter how many recordings NASA eventually releases. But mostly turned out to be doing an enormous amount of work in that sentence, because the solar system is far less empty in far more places than the flattest version of that claim ever suggested. We began with the physics itself: sound as a pressure wave, entirely dependent on a medium to carry it, and space as a spectrum running from near total vacuum to atmospheres thick enough to carry a shout, rather than one uniform, silent void. Mars, dismissed by most people as essentially airless, turned out to have just enough atmosphere for an accidental gust of wind to register on a lander that wasn't even designed to listen for it. InSight, sitting quietly at Elysium Planitia, catching real wind through its seismometer and pressure sensor on December 1st, 2018, 5 days after touchdown. Titan, more than 1 billion kilometers further out, offered something even rarer: the only microphone recording ever made during a spacecraft's descent to another world, capturing the ordinary, undramatic hiss of an alien atmosphere rushing past Huygens' casing during its 2.5-hour fall in January 2005. Both recordings were real sound, in the strictest sense: air, or something close enough to it, physically vibrating, picked up by an instrument built to notice. From there, the story moved somewhere stranger, past the point where atmospheres exist at all, into territory where the word sound survives only because scientists built it a way in. We define sonification properly in Part 2, the deliberate mapping of any measurement onto an audible form, a practice with roots in ordinary tools like Geiger counters and heart monitors, long before it became a way to introduce the public to a black hole's data. Voyager 1's plasma instrument, never designed to detect anything acoustic, happened to catch a signal sitting almost exactly inside human hearing range in 2012 and 2013, proof played aloud at a NASA press conference. That a 45-year-old spacecraft had finally left the solar system entirely, a finding Voyager 2 would independently confirm from a completely different direction 6 years later. Saturn's kilometric radiation needed a far more dramatic translation, shifted down from deep in the radio spectrum into something that sounds uncannily like a spinning air raid siren, a genuine magnetic signal, converted rather than captured, that ended up revealing a real unsolved mystery about the planet's high-altitude winds in the process, one that took Cassini's 13-year orbital stay to even notice. And then at the far end of everything came the strangest case of all: a black hole roughly 240 million light-years away, discovered by accident in 2003, generating a genuine pressure wave in genuinely real gas, the most literal sound wave in this entire video. And yet somehow the furthest from anything a human ear could ever perceive, unassisted, oscillating once every 10 million years, requiring a scaling factor of up to 288 quadrillion just to become audible at all. Not a translation of something that was never sound. A real sound wave, doing real physical work, possibly holding an entire galaxy cluster's temperature in balance, that happened to be moving on a time scale nothing built by evolution was ever meant to register. And finally, in this last part, we turn to what happens to a discovery like that once it leaves the hands of the scientists who made it, how a careful, well-documented sonification becomes, 4 reposts later, a viral claim about something that was never actually recorded at all. Look at that whole arc together, and a single thread runs through every chapter, from Martian wind to a black hole's 10 million year note. Almost none of it exists purely for spectacle. Every recording, every sonification, started as a real measurement, taken to answer a real scientific question that only later became something the rest of us could sit down and listen to. That's the quiet thing this video has been arguing for 2 hours. Underneath all the specific facts and figures, not that space makes for good sound design, but that the universe is stranger and more genuinely audible in more different ways. Then either the space is silent, myth, or the listen to this insane NASA recording, clickbait ever gives it credit for. There's also a methodological lesson buried in the shape of this whole video, one worth carrying forward well beyond the specific topic of space audio. Almost every case covered here rewarded exactly the same habit, asking what an instrument was actually built to measure before asking what the resulting signal sounds like. InSight wasn't built to record sound and caught it anyway. Voyager's plasma detector wasn't built to prove a spacecraft had left the solar system and ended up doing exactly that. Chandra wasn't pointed at Perseus looking for a note and found one buried in data collected to study something else entirely. In every one of these cases, the sound of space turned out to be a byproduct of careful patient measurement aimed at a completely different question. Never the headline the instrument was originally built to chase, but something that fell out of doing careful science thoroughly enough and staying curious enough about the data. To notice it, that habit checking what a measurement was actually for, before accepting what it's being sold as, turns out to be useful well past the subject of black holes and wind on Mars. It's the same instinct that separates a careful science headline from a viral distortion of one, the same instinct this video spent its final chapter urging you to apply the next time a sound of space clip crosses your feed. Ask what the instrument was built to do. Ask what it actually measured. Only then ask what the resulting sound is telling you, and whether telling you is even the right way to describe what a 57-octave pitch shift can honestly convey. There's something worth sitting with, now that the full picture is in view, about the fact that none of this was ever waiting to be overheard. Every sound in this video required an instrument first, and a decision after that, a choice made by a specific team of scientists about how a measurement should correspond to a pitch, a rhythm, a tone. Nothing about the universe demands to be heard this way. A radio telescope could have stayed a purely visual instrument, its data represented only in graphs and false color images, the way most astronomical data still is. Somewhere along the way, across decades of quiet research and eventually a wave of public releases, scientists made a different choice. That some of what they measured deserved an audible form too, not because the universe asked for one, but because a human ear, it turns out, can sometimes catch a pattern that an eye scanning a printout might miss, and because, perhaps just as importantly, people connect to sound in a way that a spectrogram alone rarely achieves. That's a strange kind of authorship to hold when you think about it directly. We didn't discover that black holes sing. We discovered a real, physical pressure wave, doing exactly what pressure waves do, and then we built the translation that let it reach us as something we'd recognize as music, rather than as a line on a graph. The black hole's tone existed regardless, rippling outward through Perseus's gas for millions of years before Chandra ever launched, before Fabian's team ever pointed a telescope at it, before anyone had the faintest idea a note like that was there to find. The B-flat, the 57 octaves, the 4 minutes of audio you could press play on, that part is ours, a bridge we built across a gap the universe never intended to be crossed by anything with ears. Consider, for a moment, how much deliberate work sits underneath every single sound in this video. Somebody had to design a seismometer sensitive enough to register a Martian breeze moving a solar panel by a fraction of a millimeter. Somebody had to mount a microphone on the outside of a probe falling through a moon's atmosphere 1 billion kilometers away, on the chance it might catch a clap of alien thunder and settle instead for the quieter, equally valuable sound of ordinary wind. Somebody had to keep a plasma wave instrument running for 36 years, through a dry spell nearly a decade long, waiting for a signal that might never come. Somebody had to sit with Saturn's radio data long enough to notice that its rhythm was drifting, hemisphere against hemisphere, in a pattern nobody had predicted. And somebody had to look at 53 hours of X-ray data from a cluster of galaxies and notice a ripple so faint that a slightly less careful observation would have missed it entirely. None of these people knew, when they started, exactly what they'd find. Each one built the capacity to listen before they had any guarantee there would be anything worth hearing. Maybe that's not a small thing to have done. Every instrument in this video, InSight's seismometer, Huygens' microphone, Voyager's plasma detector, Cassini's radio receiver, Chandra's X-ray optics, was built by people who would never personally travel to any of the places those instruments eventually listened to. Nobody who worked on the Perseus sonification will ever stand inside a galaxy cluster's hot gas and feel that 10-million-year wave pass by. And yet, because of the machines we built and the choices we made about how to translate what those machines measured, something that has been happening. Silently, by any definition, a person standing nearby could have applied for longer than complex life has existed on Earth, is now something you can listen to on a pair of headphones in the time it takes to finish a cup of coffee. There's an old idea in astronomy, worn smooth from overuse but still true underneath the wear, that we are in some meaningful sense the universe's way of examining itself, matter organized precisely enough to build the instruments capable of turning back around and studying the very processes that produced it. The sounds in this video push that idea somewhere slightly stranger than usual. It's not just that we can see the universe, trace its structure, measure its age. We built the specific, deliberate machinery to let it reach us through an entirely different sense than the one astronomy has always relied on, to let a wind on another planet, a boundary crossed by a fading spacecraft, a magnetic field wrapped around a ringed world, and a 10-million-year pressure wave rippling through a galaxy cluster, all become briefly something we could listen to rather than only calculate. We are, in a real sense, the reason any of this counts as sound at all. Not because we recorded it, most of it was never recorded, in the strict sense that word deserves. Because we decided, deliberately and carefully, that a wind on Mars, a wave crossing the space between stars, a magnetic field wrapped around Saturn, and a pressure wave rippling through gas hundreds of millions of light-years away were all, in their own separate ways, worth the work of making audible. The universe supplied the physics, we supplied the ears. It's worth noticing, too, how differently sight and sound have shaped what astronomy means to most people. Images have always carried astronomy's public identity, the swirl of a spiral galaxy, the rings of Saturn caught in sunlight, the pale blue dot of Earth photographed from billions of miles away. Sound has stayed almost entirely absent from that identity until remarkably recently, not because it was less scientifically valuable, but because it demanded an extra layer of deliberate translation that a photograph never required. A telescope's image is already something like a picture, however processed and false-colored it might be. A radio signal, a plasma reading, an X-ray brightness map, none of that was ever going to resemble a picture without someone first deciding, and then building the tools to make it resemble something else instead: a tone, a rhythm, a note. Sound arrived late to astronomy's public story precisely because it required more invention than sight ever did, and that lateness is part of why it still catches people off guard, part of why a black hole's B-flat still sounds, even now, like something closer to fiction than to data. So the next time someone tells you that space is silent, you'll know the honest answer isn't yes or no. It's depends where, depends how, and depends on how far you're willing to go to listen. It depends on whether there's a medium at all. On how patient the wave is, on whether anyone has yet built the specific instrument capable of catching it, and increasingly on whether the version of the story reaching you has survived a few reposts intact or lost its nuance somewhere along the way. Somewhere on Mars right now, wind is moving across a landscape nobody has ever heard directly, except once, by accident, for a few unplanned minutes in 2018. Somewhere over Titan's frozen dunes, an atmosphere thicker than our own is still rushing along exactly the way it did the day Huygens fell through it, unrecorded ever since, because no other microphone has made that same journey in the 20 years since. Somewhere past Saturn, two spacecraft older than most of their own engineers are still sending back plasma readings from a boundary that took 36 years to reach, their signals arriving now the better part of a full day after they were sent. Somewhere above Saturn's poles, radio waves are still rising and falling in a rhythm scientists still don't fully understand, drifting slightly further out of sync with each passing season, and somewhere 240 million light-years away. Inside a cluster of galaxies larger than almost anything the universe has ever assembled, a black hole is still holding the same note it's been holding since long before there was anyone anywhere capable of building an instrument sensitive enough to notice. None of it was ever silent, not entirely. It just took longer than expected and stranger tools than anyone guessed to finally listen.